in general, there are hundreds of optical color centers in diamond. And for the talk today, I'm really just going to focus on really these NVN and NV center. And all of these optical defects are caused by impurity atoms and structural defects within the diamond lattice. Three important ones which involve nitrogen and vacancies. And vacancies are just simply point defects within the lattice, where there should be a carbon atom and there's not. So this N3 center, which provides blue emission, the NVN center, which provides green emission, and the NV center, which provides red near IR emission. And again, for this talk, I'm really going to focus mostly on the NVN and NV center, as these are the most established currently commercially. How do we actually produce color centers in diamond? Well, first we need to introduce vacancies, which is then accomplished by irradiating particulate diamond or bulk diamond with high energy irradiation, be it electrons or neutrons or protons or what have you. We then heat treat this diamond at high temperature. Vacancies diffuse, they move around in the lattice and then form complexes with the nitrogen, which gives you your color center. And then we fragment these diamonds down to the nanoscale. And there you go, we have our fluorescent nanodiamonds. I would like to briefly just highlight a recently developed technique. Our group, as well as collaborators in Italy and City University, New York, we developed a new technique of annealing, which shows that you can actually control these color centers in synthetic diamonds. So heat treating at various high temperatures very quickly can lead to these very interesting fluorescence, not interesting and novel fluorescence in synthetic diamonds. So we can create these 8 NVN centers, mixtures of green and red emitting centers, and the N3 center, which gives you this blue luminescence. It's enough of the solid state kind of physics, and I want to kind of discuss the particular features, characteristic fluorescence features of diamond, particularly if you're using it in some biological application. So for the NVN center, peak absorption is around 480 nanometers, with peak emission being around 520. For the NV center, peak absorption is around 575, with peak emission around 680 to 700 nanometers. And I wanted to give a brief comparison, the quantum yield, and to a very commonly used dye, Alexa 647, which is pretty much a workhorse dye in a lot of applications. So you can see the quantum yield for color centers in diamonds is around 0.7, or Alexa 647 is about 0.33. And then fluorescence lifetime is about an order of magnitude roughly higher for color centers in diamond as compared to this Alexa 647. So they're very suitable for these lifetime time-gated imaging applications. And just to kind of orient you with size, currently nanodiamonds are optimized kind of in fluorescence to this 40 to 100 nanometer range. There are smaller particles, but down to 10 nanometer, but they have some other additional applications, not directly just related to contrast imaging in cells. So 140 nanometer particle is about approximately the same brightness as a single quantum dot. And I did want to just reemphasize the nature of this fluorescence. So it's not that the entire particle itself is fluorescent. The particle has individual fluorescent color centers packed within this single particle, which all fluoresce. And then you get your fluorescence from the particle in that way. Quantum dots or polymer dots then emit kind of uniformly, and then fluorescent, for example, then emitting as this molecular fluorescence. So the key features of diamond, and perhaps one of the most important feature of the fluorescence of diamond color centers, are their infinite photostability. And I showed 2 examples here. This example was demonstrated by Reineck and coworkers in 2016. So this was our group recently. So what we do is we had blood clots which were labeled with fluorescent nanodiamond, and another set which was labeled with phycoerythrin. Yeah, it's another commonly used dye. So phycoerythrin is actually notable for its photostability issues. But anyways, you can see that after 30 seconds, this phycoerythrin is then almost not visible. It's photo bleached completely. In the case of Alexa 647, same after 40 seconds, you can see it's effectively bleached, but our diamonds containing NV centers are still present. And then just a general comparison of fluorescence versus time compared to several other commonly used or available fluorescent materials also shows similar decay, but of course, the NV center is stable with time. Okay, so we have photostability. The next key feature is biocompatibility. And suffice to say, there is a profound amount of literature out there which has demonstrated that diamonds are quite biocompatible. In general, I wanted to just list these here. These are a little more recent. So this has been demonstrated to be biocompatible in zebrafish, rats, primates. I believe there was also a canine study. And then there's a couple reviews here which address this biocompatibility as well. These two examples here are related to our research. These are endothelial colony forming cells which demonstrate that effectively the cell viability does not decrease with increasing dose of nanodiamonds up to 100 and even up to 128 micrograms per mil. And in here it's a picomolar concentration, but again, these are in a different cell line. These are kidney-related cells, these 293 KDR cells. This was done by our collaborators at CivTech, and this was done by our collaborators at Creative Scientists. They're in Raleigh, they're in Massachusetts. But anyways, similar results. So there is no appreciable decrease in the cell viability upon exposure to increasing concentrations of diamonds. So they're quite biocompatible. A third key feature is the functional surface chemistry. So in general, we have a very diverse scheme of surface chemistry we can do with diamond, ranging from just traditional organic to biological species. Any click chemistry is available. Grafting with polymers is available, streptavidin antibodies, and then biotin, PEG. And in general, this quick example here, I just wanted to demonstrate, we took 1 micron red fluorescent diamond particles and 1 micron green fluorescent particles. So the green fluorescent particles were functionalized with biotin, the red fluorescent particles were functionalized with streptavidin, and we just mixed them together. And then you see this aggregation, which is really the demonstration of this interaction between biotin and streptavidin over time. So it's a simplistic demonstration, but it is a demonstration that you can functionalize the surface of these particles and not interfere with the functional capability of the molecule, for example, the streptavidin. So a fourth key feature is that they are quite chemically robust. So they can withstand very harsh chemical conditions. And in fact, what this example is showing is they can withstand this tissue digestion. So you can upload or introduce particles in vivo, and then ex vivo organ analysis or tissue digestion can then allow you to see the amounts of diamond that the fate of these particles in vivo. So it's quite an interesting application. And then this fluorescent spectroscopy is kind of undeniable. That is 100% the diamond spectra. So it's quite an interesting application for allowing for a quantification and determination of fate of the particles. And lastly, I will touch on this briefly in some additional application slides, but the spin properties of the NV center, since it has a free electron spin, you can it is sensitive then to these external applied magnetic fields, microwaves, electric fields, and it's been demonstrated even intracellular temperature, which I will show on a later slide. And you can also have the ability to then modulate this fluorescence with these external fields. And this is applications in not only imaging, but also in nuclear magnetic resonance and MRI.